So, hello there, my name's Aidan Hogg and I'm from Imperial College London. And today I'm going to present a paper that I presented at Forum Acusticum on exploring the impact of transfer learning on GAN-Based HRTF Upsampling. So before we get into that, I think I should just briefly explain what is meant by binaural synthesis. And to do that, just to think a little bit about what is 3D audio. Well, 3D audio is just the audio that we hear in daily life. So some sounds are far away, some are close, some are moving, some are static, and all are coming from different directions. And obviously we have different environments that we move around in. Some can be natural environments, some can be urban, they can be indoor environments. It's just the sound that we hear in daily life. So how can we simulate this then? How can we simulate these realistic sounds? A simple way would just to have a loud spherical speaker array and to play sound from different directions, and then it sounds like it's coming from all around you. But this is not obviously that practical, and do we really need so many loudspeakers? And the answer is no. We can solve this problem using what's called the head-related transfer function. And what this tries to do is it tries to exploit the fact that we only have two ears or two sensors, and tries to create the correct sound of those two sensors so that it sounds like the sound is coming from all around you. So it's basically a filter that tries to capture how your head perceives sounds coming from different locations, or different directions, shall we say. Now, how easy is it to measure these HRTFs? If you saw in the previous picture, let me just go back, you sit normally, if you want to acoustically measure it, you sit in this rig and you play sine sweeps from different directions. Here at Imperial, it takes us about an hour to create one of these HRTFs. So how practical is it? Well, you need a controlled environment. Normally, you need an expensive setup with lots of speakers and normally a turntable, and it's very time-consuming. So one way in which we can make the experiment more practical is, can we reduce the time that it takes to measure this HRTF? So it no longer takes an hour, but it's much quicker. And one possible way to do that is to try and reduce the number of acoustic measurements we need to take by doing what's called HRTF spatial upsampling, which is what this paper sort of focuses on, and how we can improve that with transfer learning. So to start with, how do we actually do spatial upsampling of HRTFs? Well, we at Imperial use a particular approach that exploits super resolution GANs. Now, super resolution GANs have been shown to work well with images. You can see two images here. One's the original, and one's been downsampled by 4 and then upsampled. And you can see they look almost identical. So can we do the same thing with a HRTF? Well, the problem is it's not the same as an image, a HRTF. It has non-uniformly spaced measurements, unlike pixels. You normally have more measurements around the horizontal plane, for example. The HRTF obviously occupies an extra dimension, unlike 2D images. And there's also limited amounts of data, whereas when you have images, you have millions and millions of images available. To train your super resolution GAN, HRTF data sets are small in number and normally limited in the number of participants. Well, to solve some of these problems, this is what we do. So one possible solution to the extra dimension is to use a 3D to 2D projection. The rationale here is if we can project the HRTF onto a 2D surface, we can basically exploit all of the literature on 2D image upsampling. Then the second problem with the limited amount of data, if we can increase the amount of data available by creating synthetic data, then maybe we can use this to train our model, or maybe we can use transfer learning to learn at least something from this synthetic data, because we know it won't be perfect when compared to real measured data. So to look at that first aspect then, how do we project this HRTF onto a 2D plane? Well, most projections, as you know, distort the relationship between adjacent points. So if you've ever looked at a map, something like Russia, country Russia looks very big relative to its actual size, and that's because of the projection that's used. But there are some projections that try to keep adjacent points closer together and try to sort of keep hold of those relations in terms of the distance. And one of those is the cube sphere. And as I've said, it takes advantage that grid cells are uniformly sized. So you can see in the image, there's the standard polar coordinates, and then there's the cube sphere. And it doesn't actually warp the sphere too much. The difference is we end up with planes rather than a single plane. We get the 6 planes of a cube, or 6 surfaces of a cube. So what does this look like in practice? Well, this is a HRTF. This is it being projected onto a cubed sphere. The colours just represent the identity of the measurement point, but you can see how all the measurement points get mapped onto a cube. We can then flatten the cube, and we've got an image. We don't normally measure HRTFs beneath us because, one, it's not very practical, and also your body causes issues with those measurements. So we don't actually need all 6 surfaces. We can just use 5. We still have the problem that they're not uniformly spaced, but we can use something called barocentric interpolation, which is effectively a weighted sum of nearest neighbours to generate the interpolated point. And then we get what is effectively an image. It's just each pixel, rather than being red, green and blue, is the impulse response in the HRTF. And now we can upsample using all of the methods that are used for upsampling images, in theory. One thing we do need to take into account, though, is obviously these planes or these panels have a relationship in terms of their adjacent sides are connected. So we can pad each of the panels with its adjacent side, and you can see that that's what we do here to sort of preserve those relationships across the panels. And then we basically have 5 images that we can upsample. So then next, with the problem of transfer learning, well, we can then generate some synthetic data. So we have what's called parametric pinner models, which just means this is your pinner here, this part of your ear, and we can define that by some parameters, and those parameters will affect the shape of the pinner. So the particular model we used more or less can model any particular ear. And we randomly generate some pinner meshes. We stitch them to a head, a dummy head, and then we can create, in this case, we created 1,000 synthetic head meshes. To get the right parameters, they were chosen from a normal distribution, and the mean and standard deviation of those normal distributions were derived from 15 HRTFs in the data set. 15 HRTFs of ears that have been generated with real ears that have been generated with the parametric pinner model. Next thing is we do something called mesh grading, because we need to turn these meshes into HRTFs, and that's normally done using something called the boundary element method. But the more triangles that you have in your mesh, then the more computation. So we grade the mesh to make sure around the pinner it's very dense, but everywhere else it doesn't matter so much. As long as you've got almost like a potato shape for your head, you're doing fine. So we reduce the triangles from about 63,000 to 20,000, as you can see here, to massively speed up the calculation to generate the HRTF. So that's what we do next. We use mesh to HRTF, which is a bit of software that uses the boundary element method to create a HRTF from the mesh. And then we actually compare that with a mesh of someone who had their HRTF acoustically measured. And you can see the comparison in that figure there. And they're surprisingly similar. Okay, they're not the same. And that's the whole point of transfer learning, is it's not acoustically measured data. It's not going to be perfect. But hopefully there's something we can learn from these synthetic HRTFs that have been generated from the parametric pinner model. So there's obviously many different ways to do transfer learning, but they all rely on the same concept, which is you have 2 data sets that somehow share some sort of knowledge. And if you look at the figure on the right, you can see that there's this sort of first learning task, and you use data set 1, which isn't necessarily the task-specific data that you're not necessarily the task you're trying to learn. And then you have data set 2, which is the task you're trying to learn. And you're hoping that you can initialize the weights with the first data set. And hopefully the first data set contains some knowledge that is helpful when it comes to training on the actual data set that you care about. It would be a bit like if you were trying to detect sort of certain things in retina scans. You might first train on all images, because there'll be things that are true about all images that are true about retina scans, and then you would train on the domain-specific data, the retina scans, and that normally massively improves your performance. So there's different ways of doing it. There's papers that list sort of 25 different ways to do transfer learning, but there'll be more than that. But we use the most simple method, which is you just train the whole network on the sort of general data, or the synthetic data in this case, and then we don't change any of the weights or the biases, and we retrain. So effectively, we're just initializing all our weights and biases with the synthetic data, and then we retrain the network on the actual measured data that we care about. But as you can see, these are other common approaches. So what does our workflow look like then? Well, you can see here we train with the synthetic data. So we first generate 1,000 meshes, we do mesh grading, we do meshed HRTF, we map that to a cube sphere, and then we train the GAN. And then we just reinitialize all the output layers of the generator and discriminator. We obviously don't change the weights or biases, and then we take our acoustically measured data, we map that to a cube sphere, and then we train the GAN again. If you're interested in network architecture, please look at the paper. I'm not going to go into detail, but it's basically the same architecture that you would expect to see when you upsample images. And then let's start thinking about some of the results then. So we sort of did two experiments. We first thought, let's try sort of transfer learning with this 1,000 synthetic HRTFs. But we actually have some acoustically measured HRTFs as well in our Sonicom dataset, which is part of this project. And we thought it would be interesting to compare the difference. So if we use the RE dataset, which is the Acoustics Research Institute in Vienna, for the training and the evaluation, and that's the sort of domain-specific data, how much improvement do we get if we train on Sonicom with acoustically measured HRTFs or Sonicom with the synthetic generated HRTFs? And because we have so many more synthetic HRTFs, maybe it does start to answer the question a little bit, not fully, obviously, but starts to scratch the surface of the question, is it better to have more or higher quality data, so sort of acoustically measured data for this transfer learning, or is it better to have more data, so we have much more synthetic data, but it will be of lower quality? Which actually matters, because when we're generating synthetic data, we can increase the number of triangles that we have, so we can improve the quality in terms of the mesh and how many triangles it has. And obviously the more triangles we have, the longer it takes to generate the HRTF. And some of these HRTFs from meshes can take about 8 hours to be generated on a high-performance computer. So if we can reduce that and still achieve similar performance, that would be very advantageous. So this is just starting to look at some of those ideas. So let's see what we get. Well, we first look at the log spectral distortion metric to sort of compare the results. And this just looks at differences in the spectrum, as you can see in this equation. And just to look at the sort of super resolution GAN with no transfer learning and just compared to a baseline, the baseline being just barocentric interpolation, as I said before, just a simple weighted sum of nearest neighbours. This is the performance we get. And sort of barocentric is quite popular, probably the most popular, but you also get spherical harmonic interpolation as well, which is similar. These are all methods that don't have prior knowledge. They just have to use linear combinations of the data that they already have. And this is the performance we get. And as you can see, when we get to 5 sample points, which is very low, just 1 sample point per panel that we have, our performance is far superior to the barocentric. And then we thought we should compare that with just 2 HRTFs that we've selected. And we tried to pick one that worked well generally and one that worked poorly generally when compared against all other HRTFs. And you can see that they're both much worse than the upsampling method, at least with the GAN. Because ultimately, if it's easier to just give someone a generic HRTF, let's say, rather than upsampling a sort of low-resolution HRTF, then we should just do that. But these results seem to say that it's actually still better to try and upsample from 5 impulse responses rather than just giving someone a generic HRTF, which is quite interesting, I think. And then when we look at transfer learning, so we still have the super resolution GAN with no transfer learning, but if we look at now transfer learning with the synthetic data or transfer learning with the Sonicom dataset, the acoustically measured data, we can actually see that this is quite interesting, that the synthetic data actually performs better than the acoustically measured data. So it seems to be that because there is more HRTFs in the synthetic data, it actually works out better. But this is obviously just one part of the story, because this is just looking at spectral differences. what happens when we look at sort of modelling perception. Now, obviously, these aren't listening tests, but you do have objective models that try to model what a listening test performance might be. And we use this sort of recent model from Roberto to see the performance. Now, all of these need to be compared against the target, which is basically the HRTF against itself, and you'll never get 100%, because even if you use your own ears to localize or locate a sound source, you won't be 100% perfect. So that's why the target gives you sort of the best performance you can expect someone to give using this model. And as you can see, all of them perform quite similarly, apart from when you start to get down to 5 samples. Again, if you only have 5 impulse responses, the barocentric really starts to fail quite badly. Now, this is the elevation bias, which says sort of, you would expect the bias to be 0, and then obviously the standard deviation is probably slightly more important here. So although the bias is still 0 for the barocentric here, a lot of the time it has a bias either positive or negative, a max of 50 degrees, which is quite out. And then if we look at the polar error, so let's say we actually get the measurement correct, then we look at how much error do we have in locating around that point. And again, you can see that the transfer learning improves pretty much at every single step. And what is quite interesting is, even though the model hasn't been trained on this perceptual model, it was actually just trained on the log spectral distortion, you still see improved performance on these perceptual models, which is quite good. And you can see that actually transfer learning is clearly useful and clearly helping, even if only slightly. And then the last one is the quadrant error, which is just how often are you outside of the quadrant, or 90 degrees from where you're trying to locate the sound source. And again, you can see that the performance is quite similar, except when you get to 5, and then it gets really bad for the barocentric. But again, the transfer learning, especially when you've got 80 points, the transfer learning really helps to improve the performance. So whereas the GAN was actually performing worse than the barocentric, now with transfer learning, it's actually performing better than the barocentric, which is quite useful information to know. Well, thank you for listening. If you have any questions, do email me at the AXD team. And yeah, I hope you enjoyed this, and I hope you can follow some of our future work on HRTF upsampling. Thanks.